Squeal. It's the library I wrote. It's a deep embedding of SQL in Haskell. So the first thing that enables kind of the heart of Squeal is an extension to GHC called DataKinds. And DataKinds is a very, very powerful extension. It lets you do a lot of type level programming. So the first thing that it lets you do is it lets you do type level strings. So you can, if you have a laptop and you have REPL open, you can try this. Turn on the DataKinds extension. Ask GHC what is the kind of whatever string you like. And it'll tell you it has kind ghc.types.symbol. So yeah, we'll have one question, and then every other question after this will have to be at the end.
Would a type level string have to be a type level list of type level characters?
No. Okay, so good question. So the question was, is a type level string the same thing, equal to a type level list of type level characters? And the answer is no. Haskell or GHC Haskell does not actually have type level characters, sadly. There are cases where I wanted that. So this is something different. In fact, so raise your hand if you know what a kind is. Okay, so everyone. So yeah, a kind is like the type of a type. So in most programming languages, there's only one kind, right? All types have the same kind. Haskell kind of came along and said, well, we have higher kinded types. And these are types that have kind, star to star, or star to star to star, or whatever. But in fact, Haskell has much more than that. It has symbols, which aren't star at all, right? This is a type level string. It doesn't have any inhabitants at the value level. It only exists at the type level. So moving on, what else does DataKinds enable? It enables type level natural numbers. So what is the kind of 90210? It's nat. And it enables type level lists. So I can say, what is the kind of the list, and give it a bunch of types which have to be homogeneous. They have to all have the same kind. In this case, the kind star. But I could do a list of strings or a list of symbols. What else? It enables type level tuples. So here I'm going to actually turn on a couple extra extensions. Type operators lets me, it's pretty self-explanatory. This thing here is a type operator. Polykinds lets us be polymorphic in the kind. So that's what lets me say, I want this to be polymorphic in the kind of this variable. And DataKinds lets me use tuples. So here I'm defining a type, colon, 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 which takes 2 arguments. And this type, you should actually read it as kind. No, never mind, read it as type. Alias type, and then it just pairs them. So this is just a convenience notation. I could just use the pairing, but it's kind of ugly. And this is supposed to give you kind of the intuition of Haskell's double colon. You can think of this as saying this name has this type. And in fact, that's why I call these things named fields. So we can say Beverly Hills with type 90210 and ask what its kind is, and it has kind pair of symbol and natural number. What else? So in full generality, what DataKinds really enables is DataKinds. Yeah. So algebraic DataKinds. So you're familiar with algebraic data types. These are sum types and product types. Well, you can have sum and product kinds. So here I'm going to define the first very useful kind, PG type. This is going to be the kind of Postgres types. So what Postgres types are there? There's bools, there's integers, there's a numeric arbitrary precision, there's a text type, and there's a whole bunch more, but we can just stop there. The next thing I'm going to define is nullity type. So one thing that Squeal enables is that we can be type safe about whether a particular column can have nulls or not, which, you know, Haskell is famous for having maybes, and that's been incorporated in many other languages. So if we ask what is the kind of a null PG int, we'll see that it has kind nullity type. So this lets us kind of create our own type systems in Haskell, hosted in Haskell, but belonging to some other system, in this case, Postgres. And finally, I'm going to say, what is a column type? It's an optional nullity type or a required nullity type, meaning it can have a default if it's optional, but if it's required, the default doesn't make sense. So that's for inserts and updates. When you insert, I want to be able to insert default if there's a constraint there. All right, so kind synonyms, Typeln Type. So there's this new extension in GHC called Typeln Type, which is like the beginning of the journey to dependent Haskell. And what it does is enables you to define kind synonyms. So even though this says type columns type, you should read it as kind columns type. And I'm defining the kind columns type as a synonym for just a list of named fields, where each named field has type column type. And this is the type of a table, right? A table has columns. Each column has a name and a type. And similarly, we define tables type as a list of symbol and column type, and this is the type of a schema, because a schema is just a set of tables. Okay, so now we have a simple type level DSL that allows us to declare the schema of our database. And this is really the heart of Squeal. This is what Squeal does that other libraries don't really do yet. So here I have a schema with a users table and an emails table. Each one has an ID field, and the emails table is going to refer to the users table because it has a user ID field. And then you see that some of the columns are required, some of them are optional. The ID fields are optional because they're going to be serials that increase. All right, so it's not enough to be able to declare the schema. We actually want to write SQL. So we want to embed SQL. And there's two basic choices for doing embedded DSLs in Haskell. There's the so-called initial embedding and the final embedding. So initial embedding, you write an abstract syntax tree as either an algebraic data type or a generalized algebraic data type. So ADTs, if you are writing an expression AST that is just unityped, right? You don't care about saying that an expression can be one type or another. And GADTs if you have something more complex. And these are really, really good for being precise, being correct. The final embedding, you actually, instead of defining an AST as a data type, what you do is you define the AST, or not the AST, but you define the language as an interpreter of that language. So like a pretty printer or some kind of executor. In our case, because we're dealing with SQL, really we want to interpret a SQL expression as a byte string, right? A byte string that we're going to pass off to libpq, which is the C library that Postgres uses. So final embeddings, what's good about them is they're very performant, right? Because it's just a byte string underneath. And it's very extensible. We'll see how that works out. And we, instead of having constructors of an algebraic data type, we have a bunch of combinators, functions that we use to generate the final result. So I like to think about this as kind of a type-directed pretty printer slash string interpolator, or maybe strong interpolator, because it's strongly typed instead of stringly typed. So SQL is a fairly complex language. It actually consists of like 4 or more sublanguages. The obvious one is the select statements. These are the structured query language, right? That's what gives SQL its name. But there's also the data manipulation language, insert, delete, and update statements, and the data definition language, create, drop, and alter statements. And there's also data control language and transaction control language, but we won't talk about those. Okay, so how do we type the following queries? So select star from users, select ID as user ID from users, where name equals $1. So the $1 is a parameter, right? Because we can do these parameters and we can pass the byte strings to them and have that be understood by libpq. So each statement has output columns, right? In the case of the first statement, all the columns from users are going to be output. In the case of the second statement, only one of the columns is going to be output and it's going to be renamed. The second statement demonstrates, as I said, that statements can have positional input parameters. And furthermore, we want to make sure that both statements are only sensible in the presence of the schema we declared in the previous slide, right? So here's the definition of our query type. It's just a new type around byte string, and it has 3 phantom parameters, one of which is the schema, which has kind tables type, the positional parameters, which is a list of column types, and the output columns, which is a columns type. So the reason there's a difference between a list of column type and a columns type is that the parameters are unnamed, right? They're just positional, 1, 2, 3. But the output columns have names. So they're kind of like Haskell records, whereas the parameters are more like tuples. All right, so here's an example of how I would write a get users query. It's just, the important thing to see here is what its type is. So for the first parameter, it's that schema that we defined earlier. The second parameter is an empty list of column types because there is no positional parameter in that first query. And the output columns is that it outputs the ID and the name. And for the second one, we see that now our input parameters is inhabited. It has a required not null piece of text, and only one thing is output, the user ID. But this isn't really great because you don't want to have to write unsafe query and just write your query because it didn't gain you any type safety, right? You have to, well, it gains you type safety, but you have to figure this out on your own. So that's no good at all. But what we can do is start defining combinators from there. Start building up this big piece, a query, from smaller pieces. Okay, so besides query, we had the data manipulation language. A manipulation has the exact same kind as a query. In fact, queries can be considered a special case of manipulations that just don't change the state. So in some sense, I kind of like to think of the data manipulation language as kind of like the state monad in Haskell. It has a function that lets you change the state, but it also has the get function, which lets you just get the state. So that's like manipulations versus queries. So here's an insert user unsafe manipulation. So now we have something a little bit different, data definitions. Data definitions are statements that change the schema. So these are like create statements, alter statements, and drop table statements. So each definition has an input schema and an output schema, the schema before you run the definition and the schema after you run the definition. So that's a fairly simple new type. And here's an example where I just threw in the SQL that you would write to create the schema that we wrote the type for earlier. So SQL expressions are the basic atoms of a SQL statement. So now we're going to drill down to the smallest level and start building out to the big level, to the queries and manipulations and definitions. So at the smallest level, we have expressions. And again, we're going to do the final embedding, so it's just a byte string. And a condition, okay, so let's talk about the kind of expression. It has the schema, or not the schema, right? Every expression is referring to a table, but that table might be a join. It's a table expression. It might be a join of a whole bunch of tables, which means that as its namespace, it could have like table1 dot column1 or table2 dot column2. So we type that as a tables type. In some sense, this is like the difference between product and sum. If your schema is a sum of tables, right, a disjoint union of a bunch of tables, a table expression is potentially like a product of tables. It's a bunch of tables just kind of glued horizontally next to each other. So for the second parameter, we have params, right? Expressions can be parameterized. And then finally, each expression has a type. So SQL defines a condition. A condition is just a Boolean expression, and that's how we define it here. But we do something in Squeal that is more restrictive than SQL is. In SQL, conditions have trinary logic. They can be true, false, or null. And I think that's confusing, so I'm forcing everyone to use not null. And so how do we create expressions? We basically just give it the standard Haskell type class instances. So if you write 1, it'll be an expression of type integer or numeric or whatever. And there's fractional and floating and isString, so you can use string literals, you can use numeric literals. And then we have a bunch of combinators for comparison, and you can add because there's num, so it's fairly rich just by implementing the standard Haskell type classes. And then, okay, so we also need to express column and parameter expressions. So a column expression is like user ID. I want to see the user ID. So what we do here is we create a class called hasColumn. HasColumn set is basically a proof that the columns variable contains a named field whose name is column and whose type is tie over there. Okay? So as long as I have a list of named fields and I reference one of those names, it'll give me back an expression of the corresponding type. And we do the same thing for parameters, except for parameters, here we're using type level naturals instead of type level strings. Okay, so now we're going to talk about another extension, a rather recent extension of GHC called OverloadedLabels. What it does is it just enables a succinct notation for a value which is completely determined by a type level string. So you can follow along in your REPL. If you turn on overloaded labels and type applications for the first example, there's a type class called isLabel, right? And it has a function, a method called fromLabel. And fromLabel, well, that's its type signature in this case. And if you turn on overloaded labels, then it gives you this sugar that you do pound and then foo, it just turns it into fromLabel at foo. So it's just a nice sugar. So here's some examples. Let's define alias, which is just the unit type, or the proxy type, if you've seen the proxy type. This is just a proxy type for a symbol. So I can say that alias is a label where fromLabel equals alias. And similarly, I can say expression is a label where from label equals get column. Get column, remember, was the method of the has column type class. Okay, so in addition to expressions, which are like columns, we want to be able to reference tables. So that's fairly simple. The only way to create a table is to reference a table that already exists in the schema. So the has table class is the only way to get a table, and we give it an isLabel instance so that we can refer to tables using this cute notation. All right, and then the last kind of atom is a type expression. So these are used in create statements and in casts. So if you're typecasting an expression, and these are like bool is a type expression which gives you a bool, and then I can say not null. So I can say bool and then apply not null to it, and that'll give me a bool that cannot be null. All right, so let's talk about some ideas in Haskell. So first of all, there's GADTs, or I usually call them gadgets. These are generalized algebraic data types. They're like algebraic data types, which you know and love, but they, instead of writing them as sum types, you give explicit type signatures to all the constructors. So to me, it has kind of like a generators and relations feel to it. Especially if you put a constraint, right, in front of a fat arrow in one of the constructors. The constraint to me is like a relation, and each constructor is like a generator. So these are really useful for making precisely typed abstract syntax trees. Here's like the prototypical example of a GADT. It's a heterogeneous list. There's a lot of libraries that provide heterogeneous lists. The most famous is Vinyl. This one that I'm writing here actually comes from the generics SOP library, which we're going to talk about more. And what a heterogeneous list is it's basically a tuple parameterized by, you could say a functor, except it's more general than a functor, a type constructor. So here I say NP of expression, and then x's is a list, and it has a nil and a cons, just like a list, but it creates a list in the type. So this lets me do kind of tuple-y things in a generic way that I don't have to deal with each tuple in a different way. Here's a maybe even simpler example. I want to be able to alias expression. So I want to be able to like name an expression or rename an expression. So if I take an expression and I say expression as and then a label, I'm going to get an aliased expression, and then I want to host the type level string in the type itself. So now this is a named field. So here's a very complex one. So here's where joins come in. So a table expression can either be a table, or it can be a subquery, or it can be a join of anything, right? It could be cross joins or inner joins. There's a bunch of other joins, but we'll just deal with these for now. So what's going on here? When we cross join, so I did, does anybody notice anything weird about the order? Nothing weird?
I do notice that the right and the left are being put together as left plus right, but they're supplied right first.
Yeah, the right is to the left of left, right? So the reason for that is that the best way to write this in a way that looks like SQL is to write it using reverse function application. So if anybody's seen the ampersand operator, that's the way you're supposed to use this, and then it looks very much like SQL. And if you use the ampersand operator, then the second to last argument is really your first argument, and then everything before is getting applied to that argument. So I would write table 2 ampersand cross join table 1, or table 2 ampersand inner join table 1, and then this is an on condition. I couldn't use what? I couldn't use it for inner join, right? Because it has this annoying condition here that kind of gunks up the works. Okay, so let's talk about some mathy things. Okay, so an action of a monoid on X is a function act from that monoid to the monoid of endomorphisms on X. So end X is just the set of functions from X to itself. And actions are expected to respect the monoid homomorphism laws, which says that the unit of the monoid gets sent to the unit of the function monoid, which is the identity, and the operator gets sent to composition, which is the operator on the function monoid, on the endomorphism monoid. So how is this useful? Well, in SQL, if you have a table expression generated from a from clause, you modify that potentially with a bunch of modifier clauses, where clauses, limit clauses, offset clauses. And we can think of each of these as being an action. So where clause is an action of a Boolean condition, and as we keep adding more where clauses, we and them together. And if you say where true, obviously that's not going to change your select. Limit is an action of positive numbers, and if I keep adding a new limit, if it's a huge limit, it's not going to change anything because I've already limited it. But if it's a smaller limit, then it's going to be the minimum of the limits that I've done so far. And offset, well, if I offset 3 and then offset 4, the total offset is going to be 7, so that's addition. And this isn't strictly true, right? Like in SQL, you can't write multiple where clauses, you can't write multiple offset clauses, but you should be able to, so we're going to let you. Okay. And then since list of X is the free monoid over X, we can use lists in the definition, and then in the interpreter, we're going to fold those lists down to the actual SQL, right, which doesn't have this multiple limit clause option. I lied a little, and I was worried that some people would take offense that I said that list of X is the free monoid over X. This is a controversial statement in some quarters.
We're all finite lists here.
Yes, only for finite lists, yes. Because how do you append 2 infinite lists together? All right. So now we can define functions, combinators, like if I say from a relation, I'm just going to use the empty element of the monoid for each of the clauses. If I say where, that's going to modify by adding the condition that I passed to the where into my list of where clauses. Similarly for limit and similarly for offset. Does anybody see a problem here? This isn't real Haskell. This is just, I wish this was real Haskell, but that would not type check as a function. But you all understand what it's trying to say. You just need to write it a little out more. Okay, so now that we have the pieces, we can define select. It takes a heterogeneous list of aliased expressions and a table expression and gives us back a query. So here's the example. Select ID as user ID, and then we have to do this annoying thing where we say, okay, it's a list of length 1, so I have to cons it onto nil. and then from a table, and then I can where, and here we see a parameter, and you see it's being applied to the type level natural 1. So that's corresponding to $1 here. And we can add a limit and offset. And we can add more limits and more offsets, and it'll just be folded using the monoid structure. And here's just another example. Here's an example of a join, right? So here you can see kind of why we use the ampersand so that the on clause looks like the same ordering. So the hope here is that despite using kind of advanced features, it'll be usable as a beginner because it just looks a lot like SQL. And you still gain all the benefits of Haskell. All right, so now let's go to definitions. So remember that definitions are just a transformation of the schema. And what happens with definitions is that they form a category. Raise your hand if you know what a category is. JJ? So a category is like a monoid, but you can't always combine elements. They have to have the same, the source of one of them has to be the target of the other one. So here, if I change from schema not to schema 1, and then I change from schema 1 to schema 2, if I combine those, it's like changing from schema not to schema 2. So the identity in this category is just the empty statement ending with a semicolon, but nothing else. And the composition is you just put the two statements together with the space or a new line in between. Anybody see anything weird? The ordering. So this is a controversial thing in math. I've gotten yelled at by professors about ordering, and so in math you kind of think of things from going from right to left. Do this, and then do this, and then do that. But in programming, usually, not so much in Haskell, but it's certainly in SQL, you usually think of going from left to right, imperative style, do this, then do that, then do that. So that's what this is trying to encode. That's why def1.def0 is you render def0 and then you render def1. Okay, so we can define create statements, which change the schema by adding a new table. So first we're going to create a type family, which just given a type level list adds a named table to it. Or it doesn't have to be a table, this is general. So here create table is going to take an alias, which is the name of the table we're creating, a list of type expressions, which is going to be the name and type of each column, right? Each column has a name and a type. And then a list of table constraints, which I'm not going to talk too much about, but this is actually something that makes the Postgres type system in some sense stronger than Haskell's type system, right? Because we can say, I only want to allow integers between 6 and 100. And without using something like liquid Haskell, you can't really do that. So this is a definition which starts with a given schema and then appends the new table onto that schema. Does anybody see anything weird? Why did I define create to add it to the end instead of the beginning? Well, just to match SQL, but this is going to be a little bit slower in the compiler, but it won't matter during the runtime because all these types go away anyway. So here's what the create statement that we wrote earlier looks like in Squeal. So we can create the users table. It's got a serial. Remember, if you know Postgres, serial is a integer type that's auto incrementing. So it has a default, which is just 1 plus the last thing that was added. And then the name is not null text. And we add a constraint. So here's some examples of constraints. We can say a primary key constraint, or here in the emails table, we have a foreign key constraint, which says that the user ID column references the users table, the ID column in that table. All right. So now I have to talk about, so this kind of is the way that we're going to build up all the different kinds of statements that you can do in SQL. But I haven't talked about how you execute these, right? So how do you execute a SQL statement? Well, what you do is there's a library called libpq that is a C library, and there's some very nice Haskell bindings for it. So you just take that byte string and you pass it off to that library, and maybe you give it some positional parameters, and it gives you back, it gives you back a result pointer, and from that you can get rows of results. But there's an issue here, which is that the schema might change. If you write a definition, the schema might change, right? So it turns out that a monoid is not the right structure we want if the schema can change. What we want is something called an indexed monoid. An indexed monad. Not a monad, but an indexed monad. So what's an indexed monad? You guys know the joke, I guess it's a joke, it's not that funny, that a monad is just a monoid in the category of endofunctors? Yeah? I actually think that's the easiest to understand definition. I don't know why it's not funny. So an index monad is the same thing, right? So if you take the category of endofunctors in Haskell, right? And instead of saying I want a monoid object, you say I want a category, right? What's that? In math, we call that an enriched category. So a monoid or a monad is an enriched monoid, an indexed monad is an enriched category. So what does that mean? So you guys all know what a category is. You know what the Haskell type class category is. But obviously there's a more general thing. Okay, so an functor enriched category means we have a set of objects that we call indices. I, j, and k, we'll label them. For any two indices, I and j, we have a functor, mij, and I'm gonna write its kind here, star to star, or nowadays you can write type instead of star. And it's gonna have a functor instance. Okay, and this is kind of the mathy definition. We give it a identity and a composition natural transformation. So eta is like a return, right? X goes to MIIX. And the reason this is a natural transformation is because it's polymorphic in X. There's like an implicit for all X there. And composition is also a natural transformation because it has X on both the left and right hand side. And this says that if I have an MIJX wrapped in an MJK, then I can get back an MI to K. So if I go from I to J and then from J to K, that's like going from I to K. So that's composition. Sure, one question.
So what are the indexes supposed to represent, like a state change?
Yes. In fact, that's like the most prototypical example of index monads is to use them for state, and that's why we're using them here, right? We have a state of our database. So the question is, what are the indices? They can be different things for different applications. For our application, the indices are going to be schemas.
Yeah, I guess a follow-up question. Sorry.
Sure, go ahead.
Why is it two indices for one? Why not just have one index?
Because then it wouldn't be a category. Yeah. So the question was, why 2 indices instead of 1? And the answer in some sense is that we have the schema before we run a definition and the schema after. So the indices keep track of the change in the schema. What numbers? Version numbers.
Except it's actually the whole version.
Sure. Well, we should be able to do versioning with this, right? Like we could have like our old schema that we wrote 5 months ago, and we realize that we need to add some stuff. So we have a new schema, and then we just define a morphism in this category from the old schema version to the new schema version. So yeah, versioning. That's another way to think of it. Which I don't know, maybe versioning is more intuitive than, you know, enriched categories. I don't think so, but okay. So also we have laws, right? So we have, you know, the usual laws of category identity and associativity laws. Okay. So we define a connection. I'm not gonna, our connection into the database is at a particular schema. Okay, so if the schema changes, we want to get back a new connection. It's really going to be the same connection, but we want to keep track of the schema. So we're going to define a type PQ, which has a bunch of type parameters as the schema before, the schema after, some type constructor, is going to be a monad, and the return value. And all it is a function which, given a connection, gives you back in that monadic context a result and a new connection, which potentially has a new schema. So this PQ, this type, it turns out to be an indexed monad. Actually an indexed monad transformer because it is parameterized over M. So for a fixed index, that is, if schema naught is equal to schema 1, then this reduces to a normal monad transformer. And we can kind of see that over here. Well, maybe not if you are not super familiar with this style, but like here, for instance, eta is just return, and I are the same here. And then mu is just like join, right? If you kind of collapse this thing down to one thing and this thing down to that thing, then this is join in a monad. Okay, so I talked about result a little bit earlier. Result is what you usually get back from libpq when you run a statement, and it's like a pointer from which you can get rows. Or you can get, like, if there's an error, you can query the result to figure out what the error was. So define will take a morphism, right, a definition, and it'll run that definition in PQ. So this kind of embeds one category in another category in a certain sense. And indeed, we would expect the laws to hold that if you define something and then you define something else, that should be the same as defining the composition of those two statements. Okay, and then also we can run manipulations and queries. So the interesting thing to see about manipulate params is that it has this constraint here, 2 params x params, right? So remember that the manipulation took as an input positional parameters, but we don't want to, we don't have any way of generating those in Haskell. What we really want to do is just have like a normal Haskell record that we pass to this, or a tuple, right? So that's what x is going to be, as long as it obeys this 2 params constraint. And we'll talk about that a little bit later. Okay, so this index monad, it has these 2 functions. So PQ bind, if you look at it, it's the usual kind of bind, except I flipped the order because it just makes more sense that way. And then PQ then is the usual kind of like greater than operator, or actually less than. So the PQ index monad, I mean, 9 times out of 10, you're just going to treat it like a normal monad, because 9 times out of 10, you're just dealing with manipulations and queries. So it's just kind of around your program that you have to worry about index monads when you're setting things up or when you're tearing down your database. Okay. So we can, I mentioned earlier, from results, you can get the rows, right? So if I have a result, then I can get rows from it. And so we have kind of the inverse of 2params is from row. So we have this from row constraint, which says that some Haskell type Y is equivalent to some columns type from Postgres. So here's my 2 classes, 2params and from row. And this says that this Haskell type X and this Postgres list of column types, params, are kind of convertible from the Haskell to Postgres. If I have a function 2params, which takes that X and turns it into basically just a list of byte strings. Each byte string is tagged by its Postgres type. So remember, NP is our heterogeneous list. K here is the constant functor. So this is, like I said, this is just a bunch of byte strings tagged by their Postgres types. And then from row is just the inverse of that. If I get a bunch of byte strings tagged by Postgres types, I want to be able to turn that into a Haskell record. All right, so the way we do this is using generics. Generics is a really cool feature of GHC that lets you reduce a lot of code by kind of getting instances for free. And that's the idea here. If you define, a Haskell record that corresponds to what you want the return result of some query or some manipulation, then you should just be able to get back that Haskell value. And you should be able to define the from rows instance by just saying deriving generic. So you don't need to understand too much of this code. This is how the library defines the instance so that you don't have to as a user. So the slist_I is something to do with singletons. Is product type is saying, okay, so in general, if we're talking about ADTs, right? You can think of an ADT as a sum of products, right? So that is a bunch of constructors, and each constructor can have like a record after it. But in the case that we're dealing with, we just want records, right? There's no sense in which a row from a table is like a Haskell record. It's not like a Haskell sum type. So we can just restrict ourselves to records by saying is product type. And then this all zip 2-column param x's params is saying that if I go one by one through this list, right, is product type x's says that the Haskell type x is a product of the Haskell types x's, and all zip 2-column params x's params says that if I go one by one through these fields of the record, each one has a type which is convertible to that Postgres type. Okay, and the cool thing was that like this definition here, it's pretty ugly, but it just falls right out. Like it's the only thing you could write, and it's a lot shorter than a lot of other generic code you might look in a code base and find. And that's because I used the generics SOP library, which is very, very good for thinking about Haskell types in this sum of products conception. And then this is the other side. And so this is the from row. And the only difference really is, well, first of all, it's reversed, right? Instead of converting things using from, I'm using to. And then I have this extra constraint that the Haskell type and the results type have the same field names. So on the Haskell side, you're going to want to give them the same field names as you gave to your table or to your query. Okay, any questions?
Can you, I know in Postgres, you can include a one select statement as basically a table and a second select. So I can go, select blah from open parentheses, select blah from blah, blah, blah,
Mm-hmm.
close parentheses, add whatever. Can you do that with this code? Or how do you deal with?
Yeah, that's what subquery here is doing. So if I have a query, that's the select, that's the inside select, then I can say, I can define a from that query as, and give it a name.
Okay. Thank you.
How bad do the error messages get if you make kind of mistakes?
They're beautiful, and they will tell you everything about what's wrong with your program, and it's very, actually, it's pretty nice because, so I mean, there's some things that are not nice, but there's some things that are nice. Inference is decent. Sometimes you have to write type signatures. Sometimes you don't actually have to write them at all. But it's always good to write them just for documentation, if nothing else. And the errors guide you to where the problem is. Hopefully, I haven't actually used this in production. You guys should do that. I developed this after using other database libraries in production, and the errors there are monstrous. I won't name names. I think, yeah.
So at one point you said with the unary list, so singleton list, you still have to constant onto nil. Why not use a type family? Like a closed type family to do that.
I'm not sure, because that's at the data level, so I'm not sure. We're defining at the data level, and it looks ugly, but at the type level, it actually looks not bad, right? It's just a singleton list, right? So you don't really need type families there. It would be nice if we had a better notation for these heterogeneous lists. I totally agree with that. I think maybe there might be a nice way to do it with template Haskell or something, but I haven't really investigated. Yeah?
It was supposed to be this fancy overloaded list. I don't know if it got into GHC or not, so you might want to.
There is an overloaded lists extension to GHC, which is actually a cool feature. And I might use it for something else, like for vector types for Postgres vector types, which I haven't actually added yet. But it's not usable for heterogeneous lists, unfortunately, because the way it doesn't just overload nil and cons, which is all I want, right? Like an extension that overloads nil and cons would be perfect. But what overloaded lists does is it has a to list or a from list function, and it just fills those in. It just, when you write a list, it changes it to from list that.
That's not the version I was thinking of.
Oh, is there something else?
The version I was thinking of was specifically designed to work with heterogeneous.
All you would need, like, it would be the simplest extension ever. All it would need is to overload nil and cons, right? Yeah, that would be great. Any more questions? Yeah?
So what exactly would I gain by using this in production?
So you gain maintainability for one thing. So like now instead of writing like just SQL strings everywhere, which like if something breaks, it's SQL, so it's like another language that you have to deal with. Here it's just Haskell, so it's embedded. If you're more comfortable doing everything in Haskell, then that's nice. You get maintainability because everything's typed, right? Like your schema is now a type. And that's, I think, a really powerful idea because, you know, down the line, you want to add something to the schema, right? And now you have to change all your statements. And now the error messages have to be helpful, right? And they have to tell you exactly where you need to change your statements. And they can because it's type safe. And then also it gives you decomposability, right? Because one problem you have in production when you're doing a lot of SQL, like as strings, is you do a lot of string interpolation if you want to get like, if you want to factor it, if you want to make it more modular. And here it's just normal Haskell function, composition and using combinators.
What are sort of the boundaries of the type safety you get from this library? I've used persistent and SQL before, and it's very, very pleasant up until you run into a weird runtime error. And the balance of runtime errors to type safety is pretty great, so I'll keep using it unless something better comes about. I mean, is this like completely type safe SQL? Does it like answer that question? Or are there boundaries that you found for type safety you can express this?
So one boundary for type safety is, like I said, Postgres table constraints, right? I can't really put all of them into Haskell, although I get some of them because we get null and not null, which adds a lot of safety. I think this is very, very, very type safe. But Esqueleto is pretty awesome too. I haven't used that one in production, which is maybe by omission naming a different one. Ryan?
I might have missed this, but do you have a way at type level to witness the fact that joining across foreign key doesn't potentially have nulls on one side?
Yes.
Is that on?
It's not in a slide, but I'll show you later. You might actually help me on that because I'm not sure I got the like logic correct. So, yeah.
Well, one thing about final embeddings, as they're normally defined, is a lot of their flexibility for the user comes from the fact that the smart constructors or whatever are overloaded. The class, do you have that, or do you plan to have that in a future version? You just left it off these slides for.
So some of them are. We saw a bunch of type classes, and that's like some of that idea. There isn't really a different interpreter there is potentially, right? Like maybe I want like a really good pretty printer that's colored, and maybe I want like another interpreter that like is just a logger, or like, I don't know. But so we saw that there's some type classes like num and fractional for the expression type, and but in general, I didn't see too much value in that. The main value for me for final embedding here is extensibility, right? Like a big thing that you need if you want to do SQL is like, what about all the cases that I didn't think of, right? And you as a user are like stuck. Well, here you can just say unsafe query and write your SQL as normal. And then you can, post an issue on GitHub for me to make a nice combinator for that. Order by, yes. For the sake of making this talk brief, I didn't include everything, but there's order by, there's grouping and aggregation, which is actually a very complicated and interesting story that took me like, I had to puzzle on that for like 2 or 3 weeks, and it was really hard.
When I went to do a SQL library for another language, order by was just, I expected aggregation to be complicated. I did not expect order by to be that complicated.
There's one complicated thing about order by, which is that in Postgres specifically, there's 2 senses in which these expressions make sense. Either they can be referencing the output list of a select, or they could be referencing the columns of your table expression.
Yes, and that's not just specific to Postgres, but
Oh, really?
Different databases have different ways of disambiguating.
Yeah.
So that complicates things.
Yeah, it's a mess. So in Squeal, the order by is referencing the table expression. And if you happen to name a output the same as a column name from your table expression, then, woe be unto you.
I
So not really, because the types aren't encoding enough information to claim that like obviously you can have two unequal statements that have the same type as a query, right? As long as the inputs look the same and the outputs look the same, doesn't matter what the, like, you add a where clause, it's not going to change the type. So I'll have to read that paper and see if there's something that I can add to Squeal from it. Maybe, yeah. So optimization is a really cool story if you're writing your own database, which...
It's more about when someone writes a SQL expression that could be
a better way. So from my perspective, that's libpq's job, that's Postgres's job. But yeah, there's definitely, well, for that, I would prefer something like an initial embedding. And I've written before a version of a SQL that used an initial embedding, and I did these kinds of optimization steps, and there it's very useful for, because there it's very precise. Initial embeddings are very precise and closed, and final embeddings are very like open and extensible. We good? Time for drinks?